So hello, ladies and gentlemen, dear former student colleagues and friends. Welcome to our presentation about overall vehicle concept, safety and reliability. Today we want to talk about data-driven approach for general development and especially race car development and engineering. My name is Markus Bleschberger. The handsome gentleman right next to me is Christian Ablasser. And yeah, he's very eager to already start with his first topic, which is overall vehicle concept and how to define the right goals for your season. So please, Christian.
Okay, perfect. Then let's start with the presentation. So at the beginning, what is a goal? So is it at Formula Student a goal to have the funniest sticker, or is it to be on the podium at the dynamics, the static discipline, or on the oval podium? So for the goals, you can define at the beginning of your season, at the beginning of your team, you can define long-term goals, which are over a longer distance period of your team, which is over several years, which can be a development roadmap from now where you want to be in 3 years, and the short-term goals would be like, for example, like season-based, where you want to be on the season. And finding the right goals is not always that easy. So it's like you can do analysis your strength and weaknesses from the past seasons. You can benchmark against other teams, what you are doing and what other teams are doing, or you can also do some at the beginning of the season, doing some internal team workshops to prioritize your team goals. And of course, for having good goals, you should make goals measurable with the SMART approach. The SMART approach is defining goals which are specific, measurable, achievable, relevant, and time-bound. For example, you could set like a goal for the next season, like being in the top 10 of the endurance at FS Alpe Adria or FS Austria. And for that to be measurable, you can have a look for the lap times which were run on the competition, and you can define, okay, I have to be under a certain amount of seconds for achieving that goal. And then if it's achievable, it's based on your resources, which you have to quantify then afterwards if it's achievable for your vehicle. And it should be also relevant. So it should be relevant to the Formula Student competition, and time-bound is also if you're saying it, for example, next year at FSR 2025 or Alpe Adria 2025, it's also a time-bound goal, for example. And here is also for the long-term goals definition an example. For example, it would be the example you are at the moment a combustion car switching to an electric car. In the first year, switching from CV to EV, building your own battery, your own inverter, your own motors, and implementing a torque vectoring control system would be like in 1 year and target for a team, which is, I think, it's barely achievable. But if you're setting up a 3 years development plan, for example, to start with building your own battery, starting with an inverter which you're buying from a company and motors from a company, and after the years setting up to develop more things by your own, it's easier to achieve than to say like I want to do it within 1 year. And then we are coming to the overall vehicle concept. So what is the overall vehicle concept? The overall vehicle concept is the big picture of your development road of your car. So it's focusing on with that you're focusing on the main parameters of your car, which is the size of the car, the weight of the car, the aerodynamic values of the car, and the design philosophy of your car, and that's your basic ground. That's your ground base for the design process for coming to the submodules and to the single components of your car. Here the guiding principle is like with the design philosophy to set like your competitive goals, which is for example for performance, simplicity, or innovation. And you can implement like a design philosophy, complex but simple. With that means it's like you can have complex solutions on the parts and components where it really matters from performance point of view and reliability point of view, and on other parts, for example, and components, you can do the keep it simple strategy to use more straightforward solutions, which are components which are less influential for your performance and for your performance of the car. And so, and how to get the overall vehicle concept. So you can use some effort for the goal quantification. It's like at the beginning you can do a point analysis after your season for weighting the disciplines to the overall competition to see like where were you performing how by how much, and with that you can also use for getting an for identifying the key performance factors of your car. You can use lap time simulations. That must be also not like an very complex 4-wheel model or 2-wheel model. Also already for identifying the key parameters, a point mass. A simple point mass can already quantify most of the key factors for your car. And with that, you can do sensitivity analysis for understanding which parameters and which modules of your car are having the greatest impact on success. So, for example, here is now an example for a points analysis from a team from a previous year where you can see the maximum points of each event and how the team was performing. And with that, you can see clearly some trends of a team where a team can improve to get more points in the competition. And with that, you can already set some targets for your next year's goals. And then regarding optimizing the overall competition performance, in Formula Student, the winner is the team which has the most points in overall. So we already got in the previous presentations how you can gain points in statics. So for the dynamics, it's like in the dynamics disciplines, you can see there's one parameter which is in every discipline, and it's the time. So in skidpad, acceleration, autocross, endurance, there is every time the time is your target, and with the time you set, you're getting your points. So you have there one parameter where you can optimize your performance for the car. And with that, you can break down your goals into the modules. So you have the parameter lap time, and you can see like the influence of the aerodynamics, suspension, tires, drivetrain, powertrain, electronics, and vehicle dynamics controls, chassis, and of course also the driver is a big influence on lap time. And so you're coming now from the team goal to the overall vehicle concept. You can subtract it to the modules, and then afterwards to the components. And that would be, for example, the process overview. So at the beginning, you're defining your team goals. Then you translate your goals into performance requirements. Then you can develop the overall vehicle concept of your car. This could be also an iterative process, since some parameters are never fixed. And then you can set the module goals and requirements for every module. And afterwards, you can define the targets for your components. And then afterwards, you can define the targets for your components. And then, so what really matters for performance? Is it like spending 100 hours developing a new display interface with a smartphone interaction? For example, that during testing, when someone is changing the setup of the car, or you are in the scrutineering that the driver can play some games with his smartphone on the display? Or is it spending 100 hours developing a new suspension kinematics? So it's up to you what to choose. But it's like for what really matters for performance is some parameters, like the first one would be the weight of the car, the height of the center of gravity, which have a big influence on the lap time of the car. The second one would be the tires and the grip. So here it is also meant the suspension grip and keeping the tire in the perfect operating window. The third one would be for the powertrain, the power of the car. Also, it's also how much power you can draw on the endurance, and the autocross has also a big influence on your lap time. And for the electric cars, yes, it's limited to 80 kilowatts, the acceleration, but if you have a drivetrain which is more efficient, you can also gain their lap time. And the fourth one is the aerodynamics. So you see quite a lot of teams running aerodynamic devices and wings. That is, of course, also has also a big influence on the cornering performance of your car. And then the fifth one is the driver. So driver is building a car without a driver who can drive with the car. is like the driver is like the connection between the car and the path where the car should go. So driver is also a very important factor here. And the sixth one, which maybe some teams are not thinking that much about, is the reliability, because to finish first you have to finish. And also in the endurance, like here now in the endurance, you can see it's like the total amount of teams in electric and in combustion engine which were running on the endurance the last five events at FS Austria. And you can see like the transparent ones. You can see like the highlighted bars are the teams which have succeeded successfully the endurance in FS Austria. And on the right side, you can see there the failure rate of the teams which are not succeeding the endurance in FS Austria. And it's for both categories. The last 5 seasons, it was over 50%. And for example, also in the electric category in 2022, for example, it was almost reaching 90% failure rate of teams which were participating in the endurance. So with that, from the reliability, it's maybe good to mention it. And I'm handing over the word to Markus, who can also introduce how to improve on reliability and risks.
Sure. Sure. I'm gonna talk about risk assessment and prioritization because, like Christian just mentioned, there is a clear maybe loss of focus on reliability in Formula Student in general, as we have seen in the past years. And yeah, the idea behind this presentation was also to give some tools, or like to give some ideas how to improve on reliability engineering and the overall risk assessment process. So I'm going to give you, or like introduce here a tool which is commonly used like worldwide, but among Formula Student teams, it's rarely really used to its full potential. So yeah, I'm very convinced if you use this tool as I presented here, you're gonna for sure see some improvement. It may vary based on your resources or circumstances, but it for sure will improve your overall risk assessment and further on reliability. So the main point I'm going to talk about here is the decision matrix, basically. It begins with the identification of the parameter. So we need to know which parameters are important to achieve our goals. So if my goal is, for example, I don't know, I want to win every competition and every discipline and want to be the fastest, of course, performance is going to be a very, very important parameter for this goal. If I want to finish all endurances and want to, I don't know, be the first one to pass scrutineering, reliability is going to be a very important one. So those parameters are very important to identify. I'm going to show you in the next slide. After that, we evaluate the parameters based on our goals. So we say, okay, performance is more important than reliability, or maybe the other way around, or even resources is a very important factor for some teams. So we're going to dive a little bit into that as well. And then after that, we have basically our decision matrix. And then we put in, like the input is our projects or our decisions. And then we can evaluate which projects should be more focused on, or which projects need more, resources, money, time, whatever. And the last part is the actual prioritization, which is the final step in this whole process of this tool. So a little case study or an example. Let's take an imaginary team. It attended 3 competitions last year. It did not finish any endurance, which is sad, so they want to change something about that. On the right side, you can see their car parameters and their results in the competitions. And they set, as Christian introduced earlier, 3 smart approach goals, so yeah, specific, measurable, and so on. First one is to finish top 10 in skidbed in FS4A 2025. The second one is the best acceleration time at any competition should be below 4 seconds, and they want to finish every endurance. Well, those goals sound nice, but now we want to know how to actually achieve them and how to quantify them, because that's what we ultimately want to do. So, parameters. I've identified 4 parameters for this team, but if you do this analysis on yourself, you may come up with different things. For example, if you have unlimited money, which most teams don't have, but let's take it for an example, resources might not be your main concern and might not be a parameter. Or if you have unlimited amount of manufacturing power and machines and so on, maybe feasibility isn't an issue for you. So this is very, very individual for your team and for your framework in that you have to work in. But let's say those 4 parameters are, I think, quite common for teams to be very relevant for them. So after I identify the parameter, I need to weigh them or like evaluate them based on my goals. Here you see a matrix. Basically, I put in performance, reliability, feasibility, and resources. And then the rows are like the goals. And then I quantify on how much impact or how important is the parameter for the goal. For example, I just take one, top 10 in skidbed FS4A 25. Performance, like 5 is the very relevant and 1 is not so relevant. 4 I take here because it's a decent improvement from last year, but it's not like nearly impossible. It's quite ambitious, but a 4 is a good score here. Then reliability, of course, you need to have some reliability in order to get to drive the skidbed, but it's not like you need to finish endurance or something. And you got 4 runs in total, like 2 for each driver. So you have some room for errors if something happens. So 2 is the adequate score for reliability, in my opinion. Feasibility, it doesn't really depend on how complex your systems are, on how you design your parts, because skidbed is a very isolated topic from that. In my perspective, this might vary if you have some special conditions, but well, this is, as I said, very individual. And the last one, resources. We might invest some things, like for example, lower the weight of the car by buying better carbon fibers or something. So we definitely need resources, but it's not the main point. I do the same for the other objectives and goals as well. And then I get basically an average score for each parameter. And as you see, reliability is the most important for this team in this situation with these goals. And feasibility is the least important. So that's exactly what I wanted to do, to actually know where to weigh my parameters and what is important for my overall goal. Next is evaluation of the projects. Now I do the exactly same, but not inputting the goals, but the projects. Here I take as an example the chassis, for example, decision if I want to keep steel tube frames or I want to make monocoques, like a very simple, simple geometry with like just put carbon fiber on it and it will hold approach, or already a very slim and lightweight and optimized carbon fiber monocoque. And those are 3 options, and there I put in already, again, I put in those inputs, I score them, and after that you can see average score is like 3.75. And in this example, in the raw scores, the steel tube makes the most sense for this team. But we have still the weighted parameters, so we multiply the parameter score with the project score, and then we get basically like a total score, which will be, as you see, 40.6 for the steel tube frame. And in this example, it's very, very clear that steel tube frame is the right decision. So this isn't rocket science at all. This is very simple to do, but you need to do it. This is the big key point. If you follow this through, you will find a lot of interesting you will notice a lot of interesting decisions that have been made in the past and may be made in the future. So I really recommend to actually try it once or multiple times, and you will see some interesting results. So to give you a little bit of a bigger picture, this whole tool can be applied to every level of the team. So we can start by the management, for example, which would be the Formula Student team and the board or whatever they are called. And they need to decide whether to put money on, like they have some money left and they want to invest or something. They need to decide, okay, do I invest it into chassis or low voltage electronics or something? And this is a decision that must be made, and with this tool you can, this helps you to decide on a data-driven base what project is better. And the same for all the other levels. Very, very important here is it's a top-down model, so it doesn't make sense if you start from the bottom and go into the the more like management level at the end, because you want a holistic approach where you actually like give an idea and this idea spreads through all the modules evenly. Yeah, also very important, the higher the level of the hierarchy is, the more level or the more depth of analysis is required, because for example, if I want to choose between two connectors for low voltage or for the wiring harness, I can make that decision basically alone, or that this might be quite an easy decision relative to other decisions. So there's not a lot of analysis needed. On the other hand, if I have to make a management decision, it's very important to have a very, very good and profound analysis of what is going on, and if, for example, chassis or aerodynamics has more potential if I just throw money at them, or if they just have a better life and have fancy carbon fiber, but it doesn't do anything. So we need to really know and quantify what improvement could be made. And this is, again, with the tools and sensitivity maps that Christian showed you earlier. There you can actually quantify how much things bringing to the table or not. Yeah, and FMEA analysis, some of you might have heard of it. I will show it in the next few slides, but this is basically a special form of this decision matrix and risk assessment. So next topic is reliability specifically. As I said, this might be a big topic in Formula Student in general. I guess most of the teams have some kind of goal in regarding reliability, or they might say, okay, I want to build a reliable car, and we want to finish every endurance, but most of the teams don't really like quantify it, like every other goal should be quantified. So I want to give here an example how to actually do reliability engineering, or at least one approach that could be useful to you. So why is reliability important? I mean, first of all, obviously it is, because to finish first you have to finish. But here you can see the loss in case of system failure is far greater than the gain if everything works out. So this, some great engineer must have said it at some point, I don't know, but it is it's very true. If in the worst case scenario you can lose so much more than you can gain if everything works fine. So it's always about risk management. And this is also very important, because this slide tells you that do not touch any projects or components where you don't see enough potential just for fun, because the risk is still there, but there might not be any potential. Okay, this is quite a good, or this is a very important point about this whole topic. So the reliability process is basically analyze, monitor, and validate. Analyze is here. We start with the goals, and Christian earlier mentioned like the long-term goals, short-term goals, smart approach goals, and he focused on the performance goals. For example, I want to finish, I don't know, top 10 in skid bed, below 75 seconds in autocross or something. But there are also other categories of goals, which are, for example, reliability. This can be, I want to be very fast and the first one to pass scrutineering and to have a car that runs 1,000 kilometers in testing, I don't know what. There are a lot of different goals that can be made based on reliability. And as with all the other goals, you need to break them down into the modules. So the goal is for each module to know how can I contribute to this goal. I mean, ask yourself the question if every module leader of your team knows exactly why and how he or she can contribute to the goal that we want to finish endurance. Does everyone know that? Maybe yes, maybe no, but this is a very important question to actually think about. Yeah. And after that, we do the FMEA analysis, which will be here. So the key point of the FMEA analysis is to find the failure modes and how to prevent it, and to quantify the risk of it happening or how big the risk is for us as a team. In this case, we have a goal like to finish endurance. And in this example, I take suspension module. And the breakdown goal for the suspension is, okay, we should have no suspension failure, obviously. But we also shouldn't have any leaking fluids. And the ride height should be constant because you could get a DSQ in post-scrutineering. Yeah? So, and maybe there are more. I don't have thought about it very into the detail. That's up to you then. So now we have this matrix, which, as you can see, lists the potential failure mode for, in this case, for example, wishbone. There can be multiple failure modes for each component, but one in wishbone is, for example, mechanical failure. The potential effects of the failure is like a DNF if there's no other option, basically. Potential cause of failure is most probably, I mean, it could be manufacturing issues, but most probably it's like wrong calculation of forces, or like the structure, the mechanical is not strong enough to withhold those forces. And the important part of this whole analysis is to give it again those scores, like severity. 1 is minimal and 10 is very catastrophic. So 5 is, yeah, it's bad but not too bad, and 10 is like really a broken wishbone and the wheel flies off or something. This is really catastrophic. So here we give it a 10. Occurrence is like how likely is it to happen. We give it a 3 because we had some, but it's not. Didn't happen that frequently. And detection means how likely is it that we detect it, like beforehand, or how can we see if this is going to happen. And this is very difficult to detect it beforehand, so we give it an 8. And the final, or like the whole process, sums up into this risk priority number. And this is the whole magic about FMEA analysis. You can quantify all the failure modes into one number, and this number says how much this component is at risk. So 0 to 100 might be low risk. You can read the categories yourself, but there's very important to note that it depends on your scale. If you, I don't know, consider a flying wheel not to be catastrophic and give it a 5 because it's not too bad, you might never reach 500 in risk score. So really, it's a relative scale, and you need to compare your results. And that's very, very important to actually get good results in the end. And yeah, the outcome of this is the higher the score, the higher the risk, and the more focus and resources we should shift towards it. Practical tips for this whole analysis is, as I said, it's always subjective. It may vary between teams, sub-teams, even people in the same module, or even the same person 2 months later. So this is really, really subjective, and it's not, so be cautious with the results and the absolute numbers. Also very important is to find the right scale, as I mentioned before. What is severity 8? It's already really bad, so a flying wheel should be probably above severity 8. And likelihood of detection 5, what does it mean? You need to find all those answers to these questions in order to get good results. And trends, not absolute numbers. As with all processes and simulations and so on, it's never about the absolute numbers, it's really about the trends. And if you see that one project stands out as to be very risky, you obviously need to focus on that. But if 3 are there up top and one has 2 points more than the other, it doesn't really matter. It's really about the big differences that you want to find out. And yeah, also as I mentioned shortly, results are only comparable if it's the same project phase, same scale of evaluation, and same level of detail as well. For example, if I make this analysis with the whole suspension part, like the whole suspension subsystem, and compare it with maybe, I don't know, some bolts or some things that are very, very into the detail, it doesn't make really sense. After that, monitoring is very important. You do this FMEA analysis, and you can see here at the very right, there's the action. So this action is like how to prevent this failure mode to occur, and as soon as you take that action, you need to monitor it. Because otherwise it's just a black box, you just try something and at the end you see if it works or not. So monitoring is very important. For example, in software, it's really important to implement debugging modes early on, because the later you do it, the worse it gets. And the worse it gets to actually know what happens to the system. So think about it early. For mechanical parts, it's mostly test benches or FEM simulations or so. So this is obviously very important, but also for this monitoring course, it's very, very useful. And yeah, for the VCU software, for example, you can also use some error messages with error codes that are very distinct, so that as soon as the error message appears, you really know what happens and in which subsystem, maybe even which error. So the better you can debug your system, the better your results will get. Then validation, also very important. You start by the component. So for example, I take the wishbone again, but I don't have anything against suspension guys, so don't worry. It applies for every other module as well. Take a wishbone, you test the basic functions, you make some stress tests or whatever you can and want to do with it. If this holds these tests, go into the subsystem, which may be the whole wheel package, for example, with the wishbones mounted already, or it might be another system. This really depends on your car and on your assembly. But yeah, there you have the first integration test and the validation of the first interfaces, which is also very crucial. If this is fine, you can go into the car, like in the standstill car, just build the whole car together and see if there's any issues or if you have any motion sweeps that you didn't do in your CAD system or some things that you didn't prepare beforehand, then you need to fix it. And as you can see, if something doesn't work, you really need to iterate and go one step back. Never go forwards and try to, or like never try to be, it's gonna be fine. As soon as we drive, it's gonna be fine. The problem will solve itself. That's never gonna happen. So always go one step back until you solve the issue, and then you can proceed to the next step. And then the last step, of course, is dynamic testing. which will be ideally simulation of the whole competition and eventually also the endurance event, which is like the highest stress situation that you build your car for. And yeah, and with that, like with dynamic testing, I think Christian has some very interesting facts about that to say, so I hand over to you.
Okay, thank you. So now we're coming to the last part, to testing. So why is testing important? It's like the importance of testing is after you have built your car and assembled it, it's like you're going to prepare for the competitions. So testing there is very crucial for identifying some issues and problems and maybe some reliability uh, some reliability issues of your car to find it out during driving. So there are three different types of phases during testing. So the first one is the shakedown test, where you just assembled all the parts which you need for your car to keep it running, for seeing if the powertrain is working and everything is working from mechanical and electric point of view is working, that the car can drive itself. And then afterwards, then the full system integration period is starting. There you're increasing the power and the load on your components step by step for getting to a competition near performance level of your car and load level of your car that you can test your car into a competition ready testing. So it's very important because it's very important to be to be to be as soon as possible in the competition ready testing, because if you, like, for example, have some components still not manufactured and starting already testing with your car, you have and then after 1 month you're getting some upgrades on your car from for example the aerodynamics. If you get them afterwards, some parts of the car, you have like some periods where your car is never finished how it should be at the competition. And for testing, to be very efficient is to set the targets the car should run in a dynamics ready state, that you can also say like the car can also positively go through the scrutineering of the car. And here in the competition ready testing, then there is the focus for preparing for the single disciplines and focus on to get as much as possible out of the car at the status after the manufacturing. So talking about testing efficiency. So the key objects for testing is to be efficient is that the car is in a scrutineering ready state as early as possible, because missing components of the car can influence the behavior of your car, and therefore it's always the target to have the parts as early as possible on the car. And it's also for being efficient. You should set yourself the target before the testing phase to have a detailed testing plan for with clear targets which you can set up for planning your testing days. Because if you are setting your targets for your test plan, the test day will start like that. At the beginning of the test day, you will discuss what to test, and with that you may go into the direction that you do some software tests, for example, for increasing the vehicle control software, but never testing an endurance, for example, before the event. So that is also another point on which you set yourself on the plan before the competitions. Plan several endurance tests where you really do it like endurance. So it's not having a total mileage over the day of 22 kilometers. That's not an endurance test. You really have to test like the first driver is driving 11 kilometers, then you do the driver swap, and the second one is doing 11 kilometers. That you really can see some reliability issues which you may have during the endurance. And also for that, since we're already talking about preparation for the competition, it's also important that before the competitions, all the drivers which are driving at the competition have enough driving time for the discipline to be prepared at the competition to know what to do. to be familiar with the car, with all the procedure for starting the car, and that they know what they have to do during that discipline. And yeah, for the preparation, at the test day, always come with a specific plan and also plan some backup options into it, because schedules are never fixed. So it could happen that that you have some problems with the car, that you also have a backup plan what to do if something is not working, for example. And do the preparation of the car beforehand. So if you can do it the night before, the day before, like stuff like, for example, VCU software flashing, doing some mechanical setups on the car, or maintaining some components, it's for the testing efficiency always better to do it beforehand if possible, because as already seen on the picture, I think everyone who was in Formula Student knows some test days where where half of the team is just standing around, the car is standing, someone is working on the car, and the other ones are playing with the smartphone and do not know what to do at the moment. And that can be maybe also improved with doing your preparations beforehand. And also for the testing efficiency, plan really some days where the car is not running on the test track for maintenance, and also for your data analysis. If you want to improve something and have the possibility to check log files, you can really set up some days where you're saying the car is not driving, where the guys really can efficiently having a look into the data. And then testing documentation. I know it's from testing not always the fun part, but it's for being in the complete development process. It's like testing and validation is the end point and gives the information for the starting point. So there is testing documentation is some stuff to do, which is then for the people afterwards and in the post-season quite good to know, and also at competition if you have to change some setups, quite good to know on which day what was set up on the car. And here is, for example, the testing documentation, a point where you track the weather data. It can be a simple screenshot from a weather app on your smartphone and implement it in a Word document, for example. Then also store with these documents the telemetry files of your car, or link it to it if you have the possibility to log files on the car. Then also a setup sheet, because every car in Formula Student is built to modify something during driving, and it can be changed because weather conditions are also not always the same. So you may have to change your setups for some weather conditions. There it's good to have a setup sheet documented, to have a look, for example, if you have a similar track temp on a previous test day at the competition, you can check the tire pressures, for example. And then also if you have video onboards, which are also sometimes quite useful for debugging if you had some mechanical failures. You maybe could see it on the video which part, for example, was the first one which was breaking, or also for the driver to see like that he can easily having a look what the other drivers at the test day were doing on the track to see if he can improve that, or if he can copy the driving style. And then also a test day log where you're writing down on every time step what has done and who has done what, and also lap times for seeing, like if you are doing, for example, in skid pad testing, if you can do some improvements with some setup changes. Then also another good documentation is the driver debrief. So the driver is actually driving with the car. He is feeling everything what the car is doing and how the car is behaving. So it's also quite important. It's a quite important information to hear to the driver what he was saying, or maybe also if he was struggling with some things on the car. And he can also tell you something about ergonomics. If there was something which was pressing on the shoulder that over the endurance test, for example, was hurting his shoulder and so on. And it's also for the driver debrief is also for driver training to compare different opinions and maybe find a middle way of a setup, for example, of the car. And then at the end of the test day, doing a team debrief for having everyone who was participating from module-wise on the test day, making with everyone a short debrief to see like They get from every module subsystem specific feedback. For example, from powertrain point of view, if the accumulate guy, which has to be on the test day because you need an ISO at the test day, who can also give some feedback at the battery. Then also component health, which you can check, and performance and reliability insights of some components, and you can also discuss, for example, some parts which have to swap for maintenance. And with that, which is also good to do, is doing a components runtime sheet. So to track the kilometers per component, so you can record the mileage for all your components, for suspension parts, tires, drivetrain, for example, the gearbox, and with that, you know, like the mileage, for example, how many kilometers you can drive with one set of tires, and then you can also put in an issue log where you document issues with components or systems that didn't perform on the test day as expected. So there, it doesn't mean that they have a failure, but just if, for example, they are not working as expected, that you document it, because then you can highlight areas during testing where you can improve, and you can set also a priority on them. And if you do this documentation, you can plan maintenance intervals. So there you can really schedule dates for replacements for some components before they are having a failure, based on the runtime sheet. So there you can ensure, for example, the reliability for critical components, because if you know, like, that one of your suspension component is can just withstand the mileage of 75 kilometers, you can already plan to replace it before you run the mileage, and maybe risking at the test day and suspension failure. And afterwards, in the post-season, you can also analyze the lifespan and the reliability of components, and then you can see already for your next development of the car the weak points of your the weak points of your car, and critical components which had some reliability issues during testing, and you can already adjust them for the next iteration of the car. And then, yeah, it's also then for the optimization for the future performance, and you can use this data to redefine the reliability goals for the next year. And I also put in a picture of a component which I once did. So sometimes it can happen that something is breaking, but it's also important to go for testing, because during testing stuff like that can happen, but you also can see it. You can also analyze it, why it happened, and it's better to have it on the test day, and maybe can have a solution until already at the competition than standing at the competition in the endurance and see your car has a suspension failure. And with that, I think that's it for our presentation. I say thank you for everyone who was watching and who was here in the room, and yeah.
Thank you very much. We are going to switch to some questions that we have. So, one of the questions is, how do you judge the effect on lap time if possible changes of your car that you cannot predict with a lap time simulation? Given that testing with the old car is also not possible.
Yeah, if I understand that correctly, for example, would be if you have a new concept, like, for example, if you're starting with from a combustion engine to an electric car, if you don't have an old car for testing and also don't have something on validation, there I think you also can have the data, for example, for electric car, for the components which you need, like the torque map of an electric car. And with that, you can already do some studies. Even if you know you didn't have the validation for that, you can already have a look. I don't put it on absolute numbers, but you can still follow the trends and see, like, how it's influencing the behavior of the car.
And maybe something to add is maybe this issue or this problem, this change, some other teams already have gone through. So maybe ask or like look for teams who may have faced the same issues or the same change in the concept, and ask them what they learned about it, because yeah, from the student teams are very open-minded to exchange information, and maybe that's your best shot you got apart from the answer that Christian gave you.
Okay, then we have just one more question, which I will answer. So the question is, when there are cars on track which are very different in speed, because one of the car might be already basically broken down and it's only limping around with 30 kilometers an hour, what can be done to prevent this? Because the faster car can only overtake in like designated overtaking zones. Yeah, I mean, so the answer is you have to look at it from our point of view, from the event point of view, and also from the point of view of the slower team. Would you like, as the slower team, to be basically dropped out of the endurance and not get a chance to score like any points in the endurance? Or would you like to have the chance to basically, yeah, limp home with your half-broken car and still get some points? We have to draw the line somewhere. We try to manage the overtaking process as good as we can. And the most important thing we do at FS Austria is limit the overall number of teams, so that basically at the end every team which can take part at the dynamics will have enough opportunity to do so. You just have to take your slot at the endurance. And that brings me to a very important topic which we always have at FS Austria. Please show up to the dynamics when they are open. It's always the same thing. We have 4 or 5 hours of endurance or dynamic runtime, for example, for the skidpad event. And all the teams turn up in the last half an hour, and then they are very disappointed when they cannot get all 4 runs in. I mean, yeah, why do you think we have 4 full hours of runtime? We need more than half an hour to get everybody through for 4 runs, so please use the available time. And the same is true for the endurance. You have to be ready when it's your time to start. When you're not ready, the next team will have to start. Then, of course, they have to be ready before they thought they would have to be. And it's a cascading effect. Yeah, and it's just be ready to drive and drive when you should. Yeah, one last segue before we get into the documentation. Adding on to dynamics stuff, please make sure when you're testing, when you're driving with your car, that you also follow some very basic safety precautions. They are to be found in the rules. But basically, you should have your impact attenuator on your car. Of course, your chassis with your main hoops has to be complete. You have to use your full driver's safety equipment. And also, of course, fire extinguishers are an important thing. And there should be somebody who can handle the fire extinguishers. It doesn't really help if you put one out on the track 20 meters away and nobody is there.
And electric safety.
Yes, thank you, Eugen. You can already come on stage. Yes, electrical safety for electrical cars is, of course, also a big issue that you have to follow for testing. And when you consider some kind of testing track, you should, of course, also make sure that you have some kind of runoff zones, and on the outside of your curves where a car could drift off, maybe it's not a good idea to park your transporter car or just sit around in the sun. Okay, thank you very much for the extremely professional presentation from our colleagues here with regards to dynamics, and we will have a direct segue into the next topic.
Ich bin zu dumm dafür.
Okay, so we had, before we start with documentation, we had some more questions with regards to mechanical and electrical. I'm filtering now for electrical. Yes, so we have the question, is it okay for the green tassel circuit to be implemented one outside of the TESAC and one in the car?
Yes, this would be okay, but consider that this stuff is scrutineering twice. So you have to show that it's working at the accumulator, at the hand card, and you have to show afterwards that it's working in the car. So this point when you have the whole logic inside the accumulator, then you just unblock the connector and you show everything's working. If you have all the electronics in the car, it might be longer time in the electric scrutineering.
So the easier way out is just to have it in your TSAC. Okay, next question. Directly for Eugen. Most TSMP banana plugs have a copper thread. Putting on a full metal lock nut will break them. I've heard of many teams that loosen the nut beforehand, which is obviously not the intent. What would you suggest?
I don't know, to be honest, I don't know. I saw the lock nuts that were working, but yeah, I don't know. Maybe I will give you an answer later. We'll have here the discussion.
So I guess this banana plug has to be locked?
The nut on the end, die Schrauben hinten.
But you could also use a tap washer for it.
Yeah, tap washer would be fine, yeah.
So maybe this is an alternative, not using a full metal lock nut, but a tap washer for this. Okay, next question. What is the intent behind rule change EV3.3 with regards to the 100 milliohm limit?
I think we had this already.
Yes, we already had it. Sorry for that. Are you able to solder a nut to a BCP to fix it in place and then screw your maintenance plug into it? Or will this be counted as a soldered connection?
To be honest, I would count this as a soldered connection.
No.
Maybe make a rule question about this, but
I think this refers to soldering in the context of the high current path.
yeah,
But this is the attachment of a PCB and not electrical connection, as I understood.
I don't know. Make a rule question. That's quite simple. That's not. Make a question with some pictures, some renderings. How this is intended.
I think the normal design is that you have a hole in your PCB and you just bolt it to some kind of metal plate or something.
Yeah. So if you only solder the plug to fix it when you start, that you can handle the screw, that's better. And at the end, it's holding by the screw, that will be okay. But I don't think that is meant here.
Okay. The explanation regarding the inverted app signal was off. Yes, okay, that is a good point. But what I drew on the page was sorry, so I have to read the question. The question is regarding the acceleration pedal position sensor, where you have to have two signals which are non-intersecting. And of course that is true with regards to the range that you have. So I drew on the page the range from 0% to 100% of throttle position. Within that range that you're using, these two signals must not intersect, so that at every point the logic can clearly say, okay, I have a valid signal, and can differentiate it from a short circuit where both signals would be shorted to the same output.
But if you mechanically limit your pedal way, the sensor has much more weight than you use, then it would be okay with. But it have to be two different sensors, and I think still with two different power supplies. It is given by some sensors on the market. Difficult to say why, because it's in the rules. We had this discussion 3 years ago, 5 years ago, when it was implemented in the rules. basically because it's automotive standard. Um, there was some error constructed that can happen. I'm also not really happy with this, so in my opinion it would be okay, but it's stated in the rules, and why not?
I think the problem is if you have basically a mechanical issue and the offset between the two sensors starts to get close to zero, then you have the problem that then again
But
the
in this case, the ECU should turn off anyway.
yeah.
Yeah. So yeah, we had a discussion a few years ago about this, and I said, yeah, okay, I don't care anymore because it's simple to implement it.
But again, if you have a very specific question with regard to your throttle position sensor, you can write this rules question anytime and attach the data sheets, and then we can give you a much more founded answer to that. Last question with regard to EVs. We have PCB bus bars made from FR4. Is this allowed? Can you please explain another time?
Make a rule question about this, and there will be a rule change in the rules version 1.1, and there will be a rules FAQ exactly about this topic, where everything will be explained. Quite good. But you can make a rule question now, or you can make it at FSG or at FS Austria as you want. It's not so easy. It's not done in 5 minutes, but there will be a solution. Nice.
Yes, and as I understood, FSG will post also some example pictures in the FAQ ticket.
Exactly.
And then it should be much clearer what we mean. Basically, there is a problem if you, quote unquote, do not use good engineering practices with regards to FR4. You could end up in a situation where you have not a proper electrical connection, and that has to be avoided. And the rules ticket will further explain that.
Yep.
Okay, we will check if we have some more mechanical questions. Yes, two. With regards to power ground effect, there is a noise limit, 106 decibels. Yes. I have to explain why did I put this in there. The power of a fan or device to move air does not have a good correlation with the maximum sound level it can achieve. So it is fully possible to have like a 500 watt device which outputs like 150 decibels of sound. So I was afraid that some teams who did not agree with our decision to remove power ground effect will turn up with 500 watts of like a sound machine, which is just blasting everybody away. So I wanted to put some kind of limit into the rules. But yes, generally speaking, it would make sense to enforce it in the same way as the current combustion vehicle limit, which is measured half a meter away from the source of the sound in some like 45-degree angle. But to be honest, if your cooling fan is louder than 106 decibels, I think you are doing it wrong, to be brutally honest. Yeah, so it was just more like a liability to make sure that teams don't make very crazy ideas. And the last question, before we go to the documents, we have how are we planning to inspect the chassis in case of a newly manufactured one? Well, that is quite easy. If you are using basically exactly the same chassis or you're using the same chassis design for a second year, we might require you to make a proof in your SCS that you actually have manufactured a new chassis. For example, you could post a picture of the newly manufactured chassis or new chassis in manufacturing process next to the old car, which has the starting number, which is clearly identifying it as last year's car. And what will restrict the tubular frame teams to just paint the old ones again? Well, the same thing. If you want to tell us that you have manufactured a new frame, you have to show us that there are at least 2 frames. And if you can only show one, then you have a problem. So, yeah, it might not be a good idea to just melt down your old car and crush it. So you should keep it around for reference in this case. Or of course you could just make significant changes to your chassis. Then it is quite obvious that you have manufactured a new chassis, and it is, yeah, you won't be asked to make a further proof.